All right, you crazy kids, here's your lecture on balancing and types of chemical reactions. For balancing, we're going to go over the theory and some tips and tricks, and then we're going to be using our knowledge on balancing in our lecture for types of chemical reactions, which is why they kind of go hand in hand. For balancing, the theory is that you need to have the total number of things reacting equal the total number of things being produced. So in this case, if I have a star-square compound reacting, and I'm producing squares and stars, that looks like it's balanced, all right? So I have one square on the left, I have one square on the right, or one square reacting and one square being produced. However, if square ends up being a diatomic, and I have a subscript 2 there, now this is fake, right? It can't happen. I've magically created a square out of nothing. So in chemistry, we balance it. And what we do is we add coefficients in front of our components of our reaction, and that changes how many things you actually have. So by adding a 2 in front of my square-star compound here, I now have 2 squares and 2 stars reacting, and I added a 2 in front of my stars on this side, so that changes how many stars I have. I have 2 stars being produced. The subscript 2 takes care of my square situation as a product, so now I have the total number of things reacting equal the total number of things being produced. In reality, it's not individual numbers of things we're dealing with it. These are molar amounts, and we're going to be dealing with that later, but that's for another day. Let's take a look at some tips and tricks. For tips and tricks, these are things I've come up with over the years that help students balance. You can use them, not use them, your choice. There's no work required for balancing, it's just whether or not you've balanced it correctly. So I guess you do you. You can use this if you want. For the first one, we have balanced non-hydrogen and oxygen elements first, moving left to right. Hydrogen and oxygen are very, very common things, and believe it or not, by balancing other elements first, they end up being balanced most of the time. So rather than dealing with them, this is a little shortcut, deal with the other elements first. Second one is balance polyatomic ions as a single unit. I'm going to show you guys an example of that in a minute. Remember, the polyatomic ions are the things that we have in our packet. You should become very familiar with them. Finally, balance hydrogen and then oxygen at the very end. Oxygen can be very tricky. It's involved in lots and lots of chemical reactions, and you end up with like uneven numbers on either side of the reaction. By balancing it last, you usually come up a lot better. All right? It's just one of those things that works. So trust me, don't trust me, whatever. Second half of our lecture, types of chemical reactions. So we are going to be doing 5 types of chemical reactions in this class today. In reality, there are 2 more, and truth be told, there are only 3 types of chemical reactions. So the 5 types we're going to be covering today are synthesis, decomposition, single replacement, double replacement, and combustion. In reality, there's 2 more types. One's called a redox reaction, and the other's called a neutralization reaction. So it's a total of 7. But there's a bit of overlap there. So truth be told, the 3 real types of chemical reactions are redox, precipitate, and neutralization. We'll get to that all later. Today, we're just going to be worrying about 5 types. These 5 types are going to help you categorize chemical reactions so you can then predict what's going to happen or predict your products of chemical reactions. This is a big skill in chemistry. It's something we're going to use all year long. Our first one is synthesis reaction. 2 or more substances combine to form a new compound. The hint here is you only have one product. All right, so a generic of this is I'm going to be taking 2 things and smashing them together. This is kind of like getting married. We'll use that example I just had. So a generic could be like, well, I'll use letters. A plus B yields AB. Okay, here's your one product on the right side of your yield sign there. You take whatever you have there and you combine it into a compound. We're going to be going over 2 different types here. You have a metal and a non-metal smashing together, and you have 2 non-metals smashing together. So for a metal and a non-metal, you should realize you're making a ionic compound. So if I had some magnesium and I combined it with some oxygen, I cannot write just MgO2. Okay, that's like bad because this is an ionic compound. With ionic compounds, remember you have to cancel out your charges. So magnesium is a +2 charge, oxygen is a 2 negative charge. So if you write MgO2, you're going to get it wrong. In reality, it's just MgO. Because that's a ionic compound, ionic compounds are solid at room temperature. So I'm going to put a little S here, and now it looks great. Second part of it is we have to balance. You'll notice that I have more oxygens on the left than I do on the right. So I'm going to put a 2 to balance out my oxygens here. And I'm also going to put a 2 to balance out my magnesiums there. Now we have the same number of things reacting and being produced. For a non-metal and a non-metal, this one, believe it or not, you're literally just going to put them together. So a nonmetal might be carbon, and another nonmetal might be oxygen. Whatever it is, you're not going to worry about the ratio. You're simply going to be combining these two things. All right, so you're going to make CO2 here. This is also how you make carbon monoxide gas, but I'm not going to expect you guys to know that that's possible or whatnot. So if you have a situation where you have a nonmetal and a nonmetal, you're literally going to combine them together. I know that, the state of matter of these two nonmetals because I know the state of matter based upon the periodic table. However, the state of matter of covalent compounds at room temperature is most likely gas. The only one that's not going to be gas is going to be water. That's going to be liquid. Besides that, anytime you have two nonmetals coming together to make a covalent compound, that's going to be a gaseous covalent compound. One of those things. All right, our next type. Instead of combining two things together, we're going to be tearing things apart. This is called decomposition. In decomposition, you have a single compound that produces two or more products. The hint here is you only have one reactant, so it's legit the opposite of that synthesis reaction. I'm going to have AB breaking apart to A and B. That's our generic. Maybe I'll put that next to generic. Cool. We have a bunch of different types here. You're going to have to do some flashcards or some memorization for your different types of decomposition. What do we have here? We have a total of 4. The easiest of the 4 is a binary decomposition. Binary decomposition means only two things are going to be bonded together. So you're going to start out with a 2-element compound, maybe like H2O. All right, H2O, a little cursive L there. That's a terrible L. Let's try that again. L, perfect. In a binary decomposition, this is binary because it's only made up of two things, the compound I'm starting with. I know it's decomposition because I only had one reactant. The only thing that's possible for this to occur is it to break apart. So whatever it is, you're just going to rip it apart into the individual elements that make it up. You have to be a little careful here because hydrogen and oxygen are both diatomics. Hydrogen is going to be a gas room temperature, oxygen also a gas room temperature. So I have to do my states of matter, and now we have to balance again. For balancing here, it looks like my hydrogens are all set, however my oxygens are not. So I'm going to have to put a 2 here for my oxygens. That's going to change my hydrogens as well, so I have to put a 2 here. Now everything is balanced. That's binary. Our next type is a metallic carbonate. Metallic carbonates always break into a metallic oxide and carbon dioxide. Carbonate, you should be very familiar with at this point in time, is CO3, 2 negative. It's a polyatomic ion. All right. A metallic was any metal, so let's pick one. Sodium. And now I have sodium carbonate. I put a little 2 here because I have to have my charges cancel out. This is an ionic compound. Because it's an ionic compound, I also know its state of matter is going to be solid at room temperature. I'm going to break it apart. I can identify it as a metallic carbonate once again because this is a metal and this is carbonate. So a metallic carbonate is breaking apart. It always breaks into the same exact stuff, a metallic oxide and CO2. The only metal that's here is sodium. So the metallic oxide is going to be sodium oxide, Na2O. I know its state of matter because it's an ionic compound, a little S. Realize that the 2 is there because you have to cancel out your charges. And the other component of my product is going to be carbon dioxide, CO2 gas. In this case, everything's balanced. All right? If I look at my sodiums, carbons, and oxygens, I have the same number being reactant as I have being produced, so I don't have to add any coefficients. That looks great. Let's look at the next one. Metallic hydroxide yields metallic oxide and water. So, hydroxide, once again, a polyatomic ion, something you should become familiar with, OH negative. Let's pick a metal, potassium, I don't know. So we'll have potassium hydroxide, KOH. This, once again, is going to be a solid at room temperature. I know that because it's an ionic compound. It's a 1-to-1 ratio because potassium has a +1 charge, hydroxide has a -1 charge, so just KOH works out great. The metallic oxide that's being produced, I need to find the only metal that's present. That's potassium. So I'm going to do potassium oxide, K2O. I'm going to make this solid at room temperature because it's an ionic compound. And I put that little 2 there because I have to cancel out my charges. Potassium has a +1 charge and oxygen has a 2 negative charge. The other component of my product is going to be water, H2O. And water is going to be liquid at room temperature. Little cursive L. Is this balanced? Not this time. So now we have to add some coefficients. Let's use those tricks I used before. So moving from left to right, balance everything but hydrogen and oxygen first. So I'll use my potassium. Okay, I got more being produced than I have reactant. I'm going to put a 2 here. When I put a 2 there, it changes a 2. It's like a little multiplier for everything here. So now I have 2 potassiums, 2 oxygens, and 2 hydrogens. That probably is good news for me, because now I have 2 potassiums here, 2 oxygens, 1, 2, and 2 hydrogens, 2. Now everything is balanced out. Kind of cool. Let's go ahead and delete all these things. Make this look pretty. All right. Our next one, a metallic chlorate yields a metallic chloride and oxygen. Chlorate, once again, a polyatomic ion. Let's use green this time. Chlorate is ClO3, -1 charge. A metal, we pick a metal. Potassium, why not? I already did that one, but it still works. So do KClO3. It's going to be solid room temperature, a little S. It's a 1-to-1 ratio. Potassium is a +1, chlorate's a -1. I'm going to break this into a metallic chloride and oxygen gas. The metallic chloride has to have the only metal present, still potassium. So our metallic chloride is going to be KCl. It's going to be solid room temperature because it's an ionic compound. Oxygen is a diatomic, and it's a gas at room temperature. Looks like that. Is this balanced? Ooh, not this time around. Well, let's see what happened here. Let's use purple. Potassium looks good, chlorine looks good. However, my oxygens don't look good. I got 3 on this side, 2 on this side. The common value between those is going to be 6, so if I turn them both into 6, at least my oxygens will work out. That's going to be putting a 3 here and a 2 here. So now I have 6 oxygens on both sides of my equation. However, now I have more potassiums and chlorines, so I'm going to put a 2 right there. If I were to ask for how this is balanced, you would simply reply 2, 2, 3. And that lets me know just the coefficients on how this reaction is balanced. All right, once again, you just got to memorize these, okay? So you're going to make some flashcards for binary, metallic carbonate, metallic hydroxide, metallic chlorate. You're going to be predicting the products, meaning I'm just going to give you this, and you're going to have to tell me this. All right, so heads up on that. Our next type is going to be single replacement. In a single replacement reaction, one element replaces a single element in an aqueous solution. So it has to be in solution. This doesn't just happen crazy in nature in a dry desert. Good example there, Rich. All right, let's take a look at our hint. A hint is an element plus a compound. So an element would be like that, and a compound would be like that. And what happens here is you're going to have this element kick out a similar element in an aqueous solution. So that means this has to be an AQ, and the element is whatever the element is. Let's pretend like A is a solid. If that's a solid and that's an AQ, the A is going to come and kick out something similar. We'll say B is pretty similar. So if B is kicked out, it means I'm going to have a new compound called AC, and B is going to be isolated. AC has to be AQ, and B is whatever it is its normal state of matter. Maybe B is another solid. All right, that's what your generic looks like. You have 2 choices here. You have an active metal replacing a less active metal, and you have an active halogen replacing a less active halogen. We have to use our activity series to make sure that this thing works. The activity series, I've kind of shown you here, is in your packet. Notice how we have very active metals up top and not very active metals on the bottom. Gold is on the very bottom. It's like you can have a gold tooth because it doesn't react with anything you're going to eat. It doesn't explode in your mouth. If you had a lithium tooth, God, that would be so bad. As soon as they put in that lithium tooth, your mouth would legit explode. Not very good. So if the individual element is a metal, and I'm talking about like this thing right here, you're going to use this side of the chart. If it is a non-metal, so if A was a non-metal, you would use this side of the chart for non-metals. That's how that coding system kind of works. All right, let's get back at it and show you guys an example. So an example of this might be, I don't know, let's make something up. Maybe some lithium reacts with some sodium sulfide, AQ. All right, so here I have the generic, all right, an element plus a compound. Lithium is a metal, so this is going to fit our active metal replaces a less active metal. All right, so what happens here? Well, our lithium here is going to come and kick out our sodium, like that. We have to cancel out our charges and make sure the whole thing kind of works still. So lithium is a +1 charge. Sulfur is a 2 negative charge, so I'm going to get Li2S. And this is, again, going to be AQ. It has to be an aqueous solution. and then my sodium is kicked out and left by itself. And sodium, when it's alone, is solid room temperature. That's possible because lithium is more active. Well, let's do it a lot smaller. Lithium is more active than sodium. All right, that works. Because lithium is more active than sodium, lithium can replace sodium. If it was reversed, it would not work. So, if I was a tricky person, and you guys should probably know that I am by now, I might give you a situation in which a single replacement reaction does not actually occur. That would look like this. If I put some sodium metal into a lithium sulfide solution. Now looking at it, because sodium is below lithium, it does not work. What you would have to write is NR, or reaction does not work. No reaction. I'm going to be tricky on that. I'm not going to be tricky on your decomposition or your synthesis reactions. You're just going to assume that's going to happen, even though sometimes they don't. But for single replacement, you get a heads up and actually look at that activity series. All right, I will try to trick you, and I will put one of these on a test or a quiz that simply does not work, and you're going to write NR. All right, so that's when a metal replaces, an active metal replaces a less active metal. The other option here is an active halogen can replace a less active halogen. And that would be your nonmetals on the side of your chart. Let's take a look at one of those. Maybe I'm going to take some fluorine gas and bubble it through, I don't know, maybe some salt water. All right, so now that I have fluorine, I'm going to be looking at this and my other nonmetal. All right, the nonmetal replaces a nonmetal, or an active halogen is going to replace a less active halogen. Is fluorine more reactive than chlorine? Well, yes, it is. All right, fluorine is higher in the chart than chlorine. Because fluorine is higher in the chart than chlorine, this can happen. It's possible. All right, so I got to match my charges here. I'm going to have sodium fluoride, AQ, and some chlorine gas. And that's how that works. Bit of a situation here is it's not balanced. All right. Oh, is this one up here balanced either? Oh, it's not. Oh, gross. Let's look. Lithium. Oh, I need a 2 here. All right. Is that everything's balanced now? How's it look? Sodium, I got 2 here. Oh, nope. Need a 2 here. All right. How about sulfur? I got 1 here, 1 here. Oh, good. So 2 lithiums, 2 sodiums, 1 sulfur. 2 lithiums, 1 sulfur, 2. Oh, need a 2 here. What happened to that 2? I thought I already drew it. Anyway, so that one's balanced. That's kind of how that works. Let's take a look at this one down here. All right, fluorines, I got 2 reacting, 1 being produced. Got to put a 2 there. Sodiums, I got 1 reacting, 2 being produced. I got to put a 2 there. Chlorines, I got 2 and 2. All right, let's take a look. So we got 2 fluorines, 2 fluorines, 2 sodiums, 2 sodiums, 2 chlorines, 2 chlorines. All right, that's balanced out. That looks great. Our next one is a double replacement reaction. So ions from 2 aqueous solutions combine to form a precipitate. Whew. A generic for that is going to be like AB, AQ, plus CD, AQ. So I'm going to have compound plus compound. And what happens here is that the ions kind of switch places. So the ions of A and C are going to switch. Right, so C is now going to join with B, and A is going to join with D. So if that looks normal to you, that's great. C's in this case and A's would be metals, and B's and D's would probably be nonmetals. So you're switching the 2 metals, or you're switching the 2 nonmetals. Either way, hopefully it makes sense. I'm going to write that as CB plus AD. Now, the big thing is here, one of these has to form a precipitate. The other one is most likely going to be AQ. We're going to check that precipitate using our solubility table. This is table E in your packet. If we look up top here, it kind of gives you a code. AQ is aqueous, dissolved in water, and S does not dissolve in water. That means it's going to precipitate out of solution. I'm going to use this example to kind of show you how that works, and hopefully it'll make sense to you. So here we know this is a double replacement reaction because I have compound plus compound. They're both in solution. I have 2 AQs. What's going to happen here is the Ag is now going to combine with the CO3, the carbonate, and my potassium is going to join in with my nitrate. So I'm going to be switching them around. This is going to produce KNO3. You might ask, well, why is it not K2? Well, it's because potassium is a +1 charge and nitrate is a -1 charge. You're making ionic compounds. You have to cross and drop your charges to make neutral compounds. And then we're also going to have Ag2CO3. I don't know if these are AQ or if these are a precipitate. So what I'm going to do is look on my solubility table for these two things and see if one precipitated out of solution. So one of them was potassium nitrate. So I'm going to find potassium. Whoa, that was way too thick. Here's potassium, and here's nitrate. All right, so I'm finding where these guys kind of cross. There it is. It's an AQ. So for potassium nitrate, I'm going to rate AQ. So far, I don't have a double replacement reaction. I need one of these things to have a precipitate to have a double replacement reaction. If both of them were aqueous, it would not be a precipitate reaction. In fact, nothing would happen. You'd have a whole bunch of ions in solution, and you end with a bunch of ions in solution. You have to have a precipitate to make it a double replacement reaction. I will try to trick you again, just like I tried to trick you with single replacement, with double replacement reactions. Make sure one of them is a precipitate. If it's not, all right, if I looked this up and it was an AQ, you cross this off and write NR. But let's see if that's actually true. Hopefully I picked out a good example. Oops. All right. So for this next one, we have silver and carbonate. Let's get rid of this stuff. Here is silver, and here is carbonate. All right. So right here we have an S, and an S means a solid, or this is not, doesn't dissolve in water. So if it doesn't dissolve in water, it's going to precipitate out of solution, and you're going to put a downward arrow. So now I have a chemical reaction called a double replacement reaction. And that's how that works. We probably have to balance here as well. Here's a situation where you're going to keep polyatomic ions as a single unit. So what I mean by that is instead of splitting this up into nitrogens and oxygen, you call this one nitrate, and you look over here, you have one nitrate. That's how that works. But we're going to use the tips and tricks that I already gave you guys. That's moving left to right, doing all non-hydrogen and oxygen elements first. So let's do silver. I got one over here, two over here. Whoa, I didn't like that. That was crazy. Let's try that again. I got one over here, two over here. I'm going to put a 2 here. Great. That changes my number of nitrates reacting, right? So now I have 2 nitrates. I only have 1 nitrate being produced, so I'm going to put a 2 here. That's treating that as a single unit. Instead of nitrogens and 3 oxygens, or 1 nitrogen, 3 oxygens, I'm just calling it 1 nitrate. Let's take a look at the rest of this and see if it's all balanced out at this point in time. So I have 2 silvers, 2 silvers. I got 2 nitrates, 2 nitrates, 2 potassiums, 1 carbonate, 1 carbonate, everything balanced out. So by treating that as a single unit, it's kind of like a shortcut, and it got me to the answer a lot quicker. We got one type left, combustion. A substance combines with oxygen. So there are kind of 2 types of this. One is a hydrocarbon combining with oxygen, or you could have individual elements combining with oxygen. So here are your 2 types. Hydrocarbon, by definition, is exactly what it sounds like, hydrocarbon, or hydrogens and carbons. So if I have some combination of hydrogens and carbons, like this, I don't know, like this, these are all hydrocarbons because it's just a bunch of carbons and hydrogens. That's what it looks like. So when you have a hydrocarbon combining with oxygen, yours is going to be left with the same exact things as a product. This is going to help you predict your products. You get CO2 and H2O. For example, I don't know, let's do C3H6 plus O2. So C3H6 is going to be a covalent compound. Because it's a covalent compound, I'm going to put a little gas. And O2 is a gas because that's what it is at room temperature. I can identify this as a combustion reaction because oxygen is a reactant. So if I have oxygen as a reactant, you're going to write down combustion. Let's see what happens here. So I know my products are CO2 and H2O. As simple as that. I don't have to really think about it because I have a hydrocarbon and oxygen. That's what you get produced. This means anytime you burn stuff, you produce CO2 or a greenhouse gas. Kind of a bummer, but that's how our world works. Is this balanced? Not even close. I got 3 carbons over here. Let's put a 3 here. I got 6 hydrogens over here. Let's put a 3 here. Ooh, boy. Those look pretty good so far. Now we got to deal with these oxygens. How many total oxygens do I have on this side of my reaction? Well, I have 3. That's 6, 7, 8, 9. Ooh. I can't put a 4.5 here. That's a no-no. All right, so you can only put whole numbers as coefficients. You can't put decimals. So I have a bit of a pickle here. How am I gonna balance this out if I have 9 oxygens being reactant and only a possibility of 2? 9 oxygens producing, only 2 reacting. The trick here is you kind of double it. All right. So if I make this a 6 and a 6, that's going to effectively change how many oxygens I have being produced. So I have 6 carbons and 12 oxygens, and I have another 6 oxygens here. So in total numbers of oxygens, I get 18. And now I can put a 9 there, and now I have 18 reacting and 18 being produced. I also am going to have to put a 2 here to balance out my carbons and hydrogens. But that's how that world works. All right, we got one more example here. It's when you're burning elements. If you burn some magnesium, you're just going to treat this like a synthesis reaction. And in fact, you're going to label it as both synthesis and combustion. It's synthesis because I have 2 elements that are combining together, and it's combustion because oxygen is a reactant. So both work. So I'm going to write MgO. I'm going to write this as a solid. It's not MgO2 because I have to cancel out my charges, and magnesium is a +2. Well, that's a terrible G. Oxygen is a 2 negative, so that's why it says MgO. So to balance this, I'm going to put a 2 here and a 2 here. And if I were to identify the type, you would write both synthesis and combustion because it fits the mold for both. That was a fun lecture. Hopefully you enjoyed it. See you guys on the other side.